systematic way of simplifying the given Boolean expression. Instead of using the postulates and theorems of Boolean algebra, we can simplify the Boolean expression in a systematic way. Okay, so let us start with a very simple case. Given f of x comma y, so that means there are two variables, and what is given is the function is given in terms of min terms. The min terms are basically 1, 2 and 3. So these are the min terms that are given. So if you write it explicitly, all the min terms, so you know that 1 correspond to x dot y bar, x bar y. 1 means x bar y, then plus 2 is basically x y bar, and then 3 is basically x y. So this is the explicit way of writing all the min terms. Now you can proceed as before to simplify this expression. For example, you can see that x is common here, okay, and so you can just go. I'm not writing the reason here because we have, this is just to show you that you can do this way. Y bar plus y, and then this is 1, so that is equal to x bar dot y plus x, which is basically x plus x bar dot x plus y. This is 1, and therefore this is equal to x plus y. So by Boolean, by simplification using the Boolean algebra, you can do this always, but we saw that in some cases that procedure gets complicated. So the alternate way is a systematic approach, which we call as Carnot map, or simply K map method, Carnot map or K map method. So what we do in this approach is that we make squares for each min terms. Okay, so how many min terms are there? With two variables, there are 4 min terms. So you have two variables, x and y. X would vary from 0, 1, and similarly y would vary from 0, 1. Right? So here, this particular cell of this square correspond to the min term x equal to 0, y equal to 0. Okay, so you can denote the min term here. So this particular square correspond to m0, and then this one is m1, and then this one is m2, and this one is m3. Okay, so m3, if you look at, x is 1, y is 1. Okay, so there are only two variables, so it is quite easy, and so there is a cell or a square associated with each min term, and then so this is the first step. Construct squares corresponding to each minterm, and the variation which x can take is 0 and 1, y can take also 0 and 1, and then you start with 0, then go to 1. Okay, so from left to right as well as from top to bottom. Okay, and then you can identify each cell or each square with a particular minterm. There are 4 minterm and there will be 4 such squares, and which square correspond to which minterm you can see by values of x and y. So 0 0 means m0, 0 1 means it is m1, and so when you write the truth table, this is what we do. We have x, y, and then you can have 0 0, 0 1, 1 0, and 1 1. Okay, so this is how we say. So 0 0, so that correspond to the minterm m0, which is x bar, y bar. Then m1 is basically x bar, y. m2 is basically x, y bar. m3 is equal to x, y. Okay, so you can see m3 means 1 1, m2 means 0 1, 1 0, m1 means 0 1. So you can see that in the table. It's basically same information corresponding to all minterm. Now we need to say in the truth table, when you define the function, whether a particular minterm is present or not. So in this particular case I said these 3 are present, so which means that we will put 1 corresponding to this and 0 corresponding to, so that is how we define the function. So this is our f of x comma y. Okay, so that is 0 means that minterm is absent, 1 means that minterm is present. So how do we present it in the Carnot map representation? What we do is we put 1 in all the squares corresponding to the minterms which are present. So that is what we do. Okay, so right now we just listed out the function, just like we represent the function using truth table. This is another way of tabular way of or table, we can say, way of representing the same information but in a box. So earlier it was like a column matrix, so now it is everything is in a 2-dimensional table. Okay, now what is next? So once we represent the function, we can go to the next step, and that is to group the adjacent squares. Group the adjacent squares. So what are the adjacent squares? For example, if you are in first what do you call this square, then adjacent square means the one to the left, or one to the right and one to the bottom. So these are the 2 adjacent cells or adjacent squares. Now theoretically what do we mean by that is like keep one variable, adjacent cell are those cells in which the minterm has only variation of 1 literal. Okay, for example, if I compare m0 with m0 and m1, if I compare, m0 is basically x bar, y bar, and m1 is basically x bar, y. Okay, so the only 1 literal is varying, that is y bar is varying from y bar to y. So this is the only variation, otherwise the other literal is remaining the same. So therefore these 2 squares are adjacent. Another way you can look at it is, if you look at the one below, then you can write it as x y bar. So here also only 1 literal is varying, that is x is varying, y bar is remaining the same. So this is also adjacent. Now if you look at here, m3, then both literal are varying, therefore it is not an adjacent, okay, because x bar y bar become xy. So both literal are varying, so it is not an adjacent cell. So we can find all the adjacent cell and group, okay, make them into a group. So that is the next procedure. So let us do that. So let us group the adjacent cells. So we can group these two. That is one way I can group, and then I can group these two. So only one literal is varying. So group here they are pairs. So this is pair 1 and this is another pair. So what is let us look at what is each group, and the group should be done in such a way that all the ones are covered. All the ones in the K-map, they are covered by one of the group, at least by one of the group. You can have one particular element part of different groups, that's okay, but at least one time it should be covered. Okay, so let us now look at what is this group representing. So this pair means group of 2. So if you look at this group, you can see that x is remaining as 1 and y is varying. So it is like two terms are there. So let me write the two terms, x y bar plus x y. Now what we can do? We can do x common and then y bar plus y. So that is equal to x. So this is the simplification. We don't need to do this algebra, but you just look for what is not varying. I told you that when you group, only one variable is should remain in the adjacent cell. Only one variable will or one literal will vary. It may be complement or direct form. It may vary like that. So look for what is not varying within the group. So here x is not varying, so that itself is the expression for the group. Similarly, for this group, what is not varying is y. So that is the expression. But how does y comes? Y is basically coming from x bar y plus x y, and then you take x bar plus x dot y, which is equal to y. So this simplification is done in a systematic manner because of the way we have entered the information in the truth table such that the adjacent cells will have only one literal variation. So now finally our expression f is equal to, or f of xy is equal to sum of these. So one this and one this, so that is x plus y. So this is what we got earlier by algebraic method. What we got, x plus y, we are getting through K-map. Okay, so this is a very simple case where there were only two variables, but usually for two variables you could just simply, if you are familiar with the truth table of each two variable functions, then you can immediately write without even K-map also. Okay, let's look at a more involved case. I will take examples from the book itself. So example 2, f of, simplify this expression, x, y, z, that is three variables. Here sigma 2, 3, 4, 5. So there are three variables, min terms are given, we have to write the K-map. Okay, step 1 is to create a two-dimensional square representation for each min term. So you can do it in two different ways. You can take 2 along the x direction and then 4 along the y direction. So how many min terms are there in this three variables? For the three variables, we have 2 raised to 3 is equal to 8 min terms. So they could be either represented by 2 by 4 or 4 by 2 columns and rows. Okay, so let me just do like this. So I am drawing 2 rows and then 4 columns. Okay, so this is one way. I could also do this way. That is an option with respect to you. You can do whichever way you want. Now if I do this way, I will have 2 variables here and 1 variable here. If I do this way, I will have 1 variable here and 2 variable here. That's the only difference. And the x can take 0 and 1. Y can be 0, 0, 0, 1. Now be careful, next to 1 should be 1, 1 and then 1, 0, because we need to arrange the order in such a way that there is only one literal variation, so that it is satisfying the adjacent cell definition. I told you. So whenever you go from one cell to the adjacent cell, there should be only one literal that is varying. Okay, so if you put 1, 0 here, 0, 1 to 1, 0, 2 literals will vary. So that is should be avoided. And similarly here also 0, 0, 0, 1. Don't put 1, 0. If you put 1, 0, both literal will vary. So you put 1, 1 and then 1, 0. So that from here to here also one literal varying, here to here also one literal varying, and here also one literal only varying, and 0. So now all adjacent cell definitions are satisfied in this manner. Now you need to identify which cell or which square correspond to each minterm. So if you look at these, so 0, 0, 0 is M0, 0, 0, 0, 1 is M1, then 0, 0, 0, 1, 0 is M2, then M3. Okay, so you look at the way I went, M0, M1, M2, M3. That's because 1, 1, 1, 0 come here. Okay, minterm can be identified by just taking the code 1, 0, 0. So that is 4. So that you write M4. Okay, and next one is M5, and then M6 is here, and M7 is here. Okay, similarly you can do here also. So let me do it a little more bigger so that you can see properly. M0, M1, then M2, then M3, M4 is here, M4, then M5, then where is M6? M6 is here, M7 is here. Okay. Now the function is given with all its minterm. The next step is enter the minterms. Okay. So 2 is there. So wherever M2, you put that. 3 is there, put 1 there. 4 is there, put that. 5 is there. Okay. So out of the 8, 4 are present. So we put ones in those squares corresponding to the minterms which are present. Next thing is grouping. So here for a 3 variable came up, there are total 8 squares, and if all the squares are 1, you could group everything together and you could write the function as f is equal to 1. Okay. Now if 4 adjacent cells are 1, then you could group all the 4 also, but here that is also not, that option is also not satisfied. Only possible way you can group here is the pairs. So again, just like previous, you can group these pairs, and the moment you group in them as pairs, each group correspond to a product term in which one literal will be absent. Okay, so because pairing means you are going one level of simplification. So you get rid of one of the variable, and which variable you are getting rid of is found by looking at the pair values, what is remaining constant. So that is going to remain, but the one which changes is simplified, and we have gotten rid of that. Okay, so here if you look at x is not varying, x is remaining as 1, so x is in direct form, whereas y is remaining constant, it is remaining as 0, so it is x y bar. And if you look at z is varying, so it is like summing up z plus z bar, simplification we got as x y bar. Similarly for this you have x is remaining as 0, so x bar, and then y is remaining at 1, so it is y. Z is varying, so that doesn't come. So therefore our given function simplified version is x y bar plus x bar y, which is nothing but our XOR gate. Okay, so it doesn't depend upon z, it is basically an XOR gate operation. Okay, let's look at another example.
Excuse me, sir.
Yes.
Sir, can you please repeat once more?
Okay,
This
the first step, so let me use this one now. So first step is create columns, or create the squares for each minterm. So for 3 variables you have 8 minterms. You can have columns and rows arranged either in this way or this way. And then once you create 8 squares, enter 1 in each squares corresponding to the minterms which are present in the function. 2, 3, 4, 5 are present. So let me enter here. 2 is present, 3 is present, then 4 and 5 are present. Okay, and then what you need to do is you group. Okay, so you try to make group. So here this is one group and this is an, you group the adjacent cells. Okay, so you should look for grouping as much as more number of adjacent cell available, but sometimes you are limited by the location of the ones. So in this particular case, the grouping that is possible, the biggest groups that are possible is making them into pairs, and each pair corresponding to one product term, and which product it corresponds to, look for what is not varying. Here x is not varying, it is remaining as 0, so x bar, and then y is remaining at 1, so it is y. And here x is remaining at 1, that is x, and y is remaining at 0, so y bar. Okay, so therefore f of x comma y is sum of these two, x y bar plus x bar y, which is basically x over y. Is that clear?
Yes, sir.
Okay, let's do more example.
So one more question, sir.
Yes.
Sir, that you have taken 8 mean terms in here.
Out of 8 minterm, only 4 are present. Right? The function definition is given 2, 3, 4, 5. Right here.
So, but corresponding to that, so you have given 8 mean terms. It means that.
No.
Is it
with the 3 variables?
Zeros also present in this.
Maximum 8 minterms are there with the 3 variables. Right? X, Y, Z. 3 variables means for 3 variables we have 2 raised to 3 is equal to 8 minterms. Out of which one are present for the given function? Only 2, 3, 4, 5.
Oh, okay, sir.
So we enter ones in the k-map corresponding to the location where the minterms are present. The one which is not present, they are absent. Okay, so we don't enter 1 there. So this is having the same information of the truth table, but in a different way we are putting it. Now here one advantage is that we have the concept of adjacent cell, where only one literal is varying. So if you are sitting here with respect to this is an adjacent cell. Similarly, left one is an adjacent cell, bottom one is also an adjacent cell, because if you compare the minterms corresponding to the adjacent cell, only one literal is varying. So that brings simplification. So let's do more problems. So this concept will clear as you do more problems. So example 3. So let's do another one. F of, again 3 variable, but here the minterms are different. 0, 2, 4, 0, 2, 4, 5, 6. Okay. As I told you, you could go constructing the K-map either two different ways, either this way, horizontally aligned, or vertically aligned, because we need 8 columns, 8 cells altogether. So let me just make like this. Okay, and here I have one variable, here I have two variables. X can take 0 and 1. This YZ can be 0, 0, 0, 1, 1, 0, 1, 1. Okay, so the order you have to be very, very careful. Only one literal should vary when you go to the next cell. Then enter in the cases which are present, minterms which are present. So you need to know, you need to identify the squares corresponding to each minterm, so that you can see by looking at the value of x, y and z. 0, 0, 0 means m0, and that is present, so I am putting 1 there. Then 0, 0, 1, that is 1, that is not present. Then 0, 1, 1, that is 3, not present. 0, 1, 0, that is 2, yes, that is present. Then 4, here it is 4, and then 5, this is 5, and then 6, 1, 1, 0, so that is this. Okay, so we made the squares for each minterm and then entered 1 corresponding to the minterms which are present in the function. This is the step 1 and step 2. Next step 3 is grouping. So we should try to make a group of adjacent cell, and we should also try to make bigger groups consisting of all the adjacent cell. Okay, and the group which are possible, so let me say that also. The possible groups, possible groupings, number 1, pairs, that we have already seen in the previous example. Next is quad. Okay, so we'll see in this example we have a quad, and then we can have octet, that means group of 8. Okay, so pair means group of 2 cells, this is group of 4 cells, and then this is group of 8 cells. Total we have 8 cells, right? So okay, octet, so octet has 8 cells. If all of them are 1, you can just make them a group of 8. Okay, when you have group of 2, you reduce 1 literal. When you have group of 4, you reduce 2 literal. Okay, so let me just show you how group of 4 will reduce to. So group of 4 is trying to say that so x bar y bar plus x bar y plus x y bar plus xy. Okay, so if you have something like this, now what you can show is that this is equal to, so you take this 2 and combine x bar into y bar plus y, and then similarly you can combine these two also, x into y bar plus y. So we know that this is 1, this is also 1, and so you get x bar plus x, which is equal to 1. So this is what happens. So there were 4 terms. When we group means we are basically combining them, and when you combine them, so each of the term are like adjacent to some other term, right? All that is why we are able to do this simplification, and in that way we got rid of 2 variables. Okay, so when you have a quad, you reduce the variable in the product term by 2, reduces 2 literals. Pairs will reduce 1 literal, and octet will reduce 3 literals. Okay, so now let's see what way you can group in this problem. So let us see whether any octet are present. No, octet cannot be present, because then all has to become 1. Then only all 8 can be grouped. Now any quad is present. Yeah, so if you look carefully, this is a quad. This is a quad, because all of them are like changing by 1 only. The neighbors are, so this and this are adjacent, this and this are adjacent, this and this are adjacent, similarly this and this are adjacent. So you can make a quad like this, and the quad will simplify the product term by reducing 2 literals. So what is the expression for this? The expression for this is basically, look for what is not varying. X is varying 0 and 1, so X will disappear. And similarly, if you look at Y is also varying. Y is 0 here, Y is 1 here. If you look at this way, Y is 0 here, Y is 1 here. So Y will also get gone through this kind of simplification. So both X and Y will go, and it will become 1. And what is not varying is Z, and Z is 0, so it is Z bar. Okay, now there is one case which is not covered by the octet, that is the 5th one. So we need to make them part of next bigger group, so which is possible. So here the next bigger group is like grouping like this. Now this will give rise to a term by looking what is not varying. X is not varying, so X will be present, and then Y is 0, so X Y bar. Z is varying, so therefore our function is basically X Y bar plus Z bar. Okay, so if you write the Boolean expression, it is a very complicated expression if you write all the main terms, but then you can simplify it into this. You cannot simplify any further, that is assured. If you do the came-up operations correctly, you will get an expression which is the most simplified expression. Okay, so most simplified means the number of terms, product terms, should be minimum, and the number of literals in each product term should be minimum. This is what we mean by simplification. Okay, so what do you mean by simplification? So simplification in SOP form is what we are looking at. So first one, the number of product terms should be minimum. Next we can say the number of literals in each product term should be minimum. Okay, so number of product terms should be minimum, number of literals in each product term should be minimum. So that will reduce the hardware requirement, like number of, so for example, number of product terms should be minimum means then the inputs to the OR gate will be lesser. number of literals in each product term is minimum means the inputs to the input to the AND gate will be minimum. Okay, so here we have only this 2 product term, so you can implement it using a 2 input OR gate, and then here we need 1 AND gate. So X, then Y bar, so that will go to an AND gate, and then you have Z bar, so this will go to an OR gate. Okay, so very simple circuit, 1 AND gate, 2 input AND gate, and 2 input OR gate. But if you look at this particular expression, you need 1, 2, 3, 4, 5. 5 input OR gate is required, and then each of this min term has correspond to 3 input AND gate. So 1, 2, 3, 4, 5. 5 AND gates will be required, and each of them has 3 inputs, and similarly 1 OR gate with the 5 inputs are also required. So all of that is now minimized, and so the ultimate aim of simplification is to reduce the hardware requirement needed for implementation. Okay, so let's do one more example and then stop for today. So let's go to say a 4 variable case. Okay. Example say 4. F of W, X, Y, Z is given as sigma 0, 1, 2, 4, 5, 6, 8, then 9, 12, 13, 14. Let me count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 terms are present. Okay, so with 4 variables, total number of min terms which are possible is 16, right? 2 raised to 4, that is 16. So we need to create a came up with the 16 squares. So let us do that. Okay, so you can see that here 16 squares are there. So 2 variables I will give here, W, X, and Y, Z I will give here. So W, X can take 4 combinations, 0, 0, 0, 1, and then 1, 1, 1, 0. So this has to be kept in mind. Don't go in the binary way, you go in a different way such that only one literal is changing from one step to the next. Similarly here also 0, 0, 0, 1 only allow one change, one literal is allowed to change, so either the first or second. So here if I allow the first one to change, it will go to 1, 0, then the second one to change, that is 1, 0. Now enter. So you need to identify which minterm is, so you can see the code here, and that is how you can identify. 0 is present, so let me put 1 here, then this is 1 is present, then 2 is present, means here 3 is absent, then 4 is here, 5, 1, 0, 1, that is 5, then 6, that is 1, 1, 0 here, 7 is absent, then 8 is here, okay, 1, 0, 0, 0, that is 8, then 9, 1, 0, 0, 1, then 12 is 1, 1, 0, 0, so 1, 1, 0, 0, this is 12, then 13, 1101 is 13, and then 14, which is 1110. 15 is absent. Okay, so this is how we do. So we did two steps. One is creating a K-map with the 16 cells, and then identifying each minterm with each square, and then second step is entering in all the minterms which are present in the given function. Third step is grouping. So look for adjacent groups with the biggest size. Okay, adjacent elements can be grouped to the biggest size, and the possible sizes are 2, 4, 8 and 16. Okay, here a group of 16 is also possible because there are 16 cells, but since all of them are not 1, we cannot make a group of 16. Next possibility is look for adjacent cell with the size of 8. Okay, a group of 8. So that is possible here. Okay, so if you look at every cell has an adjacent cell here, such that a group of 16 is possible here. Sorry, group of 8 is possible here. So now what does this product term correspond to? It is an enormous simplification that we are doing with just one big group. Enormous simplification. 3 literals will go away, and we get a product term which is single literal. And what is that? So you see W varies, X varies, then Y does not vary but Z varies. So this is basically Y bar. That's it. Okay, then no more group of 8 is possible. If this was also 1, I could have grouped this 4 and this 4 together into 1 8, but since there is no 1 here, that is not possible. So next possible way is making them group of 4, such that every one will be covered at least once. There is no point in now grouping this 4 or this 4 because they are all covered. So if at all we need to come up with a new group, it should be such that to cover the remaining uncovered ones. So that is possible here. Like we can cover these two by making a group of 4 like this. Now group of 4 will reduce 2 literals, which is also a good amount of simplification. So what is not varying? W is not varying, so W bar, because W is 0, X is varying, and then if you compare these two, Y is varying, 0 here, 1 here. Z is not varying, Z is, so you can group it like this. Now still one more 1 is uncovered, right? So that also need to be covered. So what we can do is make another group like this. So always try to make bigger group, make the one part of a bigger group, because that will lead to bigger simplification. If you just group them alone, you have to write all the four literal, or if you just make a pair, you have to write 3 literals. But if you make a group of 4, that will only have 2 literals. And then look for what is not varying. Here W is varying, X is not varying. So X is 1, and then what else? You have Z remaining at 0. So Z bar. So that's it. No more terms which are left uncovered. So therefore I can write F W X Y Z is equal to Y bar plus W bar Z bar plus X Z bar. So this is the final expression. Okay, so this is the simplified expression. We can't go beyond that. Now, is it unique? it need not be unique. You can have multiple simplified expressions possible, depending upon the way you are grouping. Sometimes there are two options which will give rise to similar amount of simplification, but giving rise different expressions, different simplified expressions. So that is possible. In this case, in this case that doesn't occur, but there would be always examples which we can find where such cases would arise. Okay, so since the time is up, I will stop here.